Hi everyone, and welcome to the third lecture of this mini course in Einstein metrics. Please, Samsung, go ahead.
No, yes. Good morning or good evening. Let's recall what we did the last time. We mainly talk about four-dimensional Einstein hyperkähler matrix. These were characterized by the fact that locally it can be characterized that as the W plus equals reach equals 0. The only curvature left is W minus. Well, I mean, by definition, it's the holonomy group contained in SU2, same as P1. And but then we said because W plus equals reach equals 0, the lambda plus is flat, and then we have a parallel triple of two forms, self-dual two forms, and then we get omega equals omega 1, omega 2, omega 3. So these are three true forms which are closed, and omega I wedge omega j equals 1/2 equals delta ij times d mu of the metric. So we have such a characterization. So we didn't finish. How do we go back from this triple two forms to the fact that this metric is hyperkähler, or it determines a hyperkähler metric, omega I. So this way, hyperkähler metric. So how do you define a metric using this three true forms? So this is first we just write down a formula. This is G omega using this, and then you have two vectors. I just defined to be this. This is Kronecker notation. So epsilon ijk equals 1 if ijk is a positive cycle, otherwise it's 0. So it's run from 1 to 3. Iota psi omega I. That's a different I. Was 1/6 I j k iota psi omega I, which iota eta omega j contract omega k divided by this is d mu g d mu. So in other words, so if we are given a triple of two forms and a volume form d mu satisfying this system of equations, then I define this metric in this way. So one has to check this is a metric. One way to see this is to use linear algebra, and this is the linear algebra factor. Is that if we are given at each point, we can choose a standard basis of the tangent space or cotangent space point. Can choose also normal basis E1, E2, E3, E4 of the tangent space, such that this omega i's are given by the standard form. So omega 1 equals the dual basis E1 wedge E2 plus E3 wedge E4. Omega 2 equals E1 wedge E3. This is what we sorry, not also, not just choose a basis. Can choose basis E2 E3. So before we said if we have a metric, then for the self-dual part, if we choose an orthonormal basis, the self-dual part is generated by the three two forms of this form. Now, suppose we are given three two forms, just satisfy this algebraic equation. And it is basically they span a basis of they span a three-dimensional positive subspace of lambda 2. So wedge product is a non-degenerate symmetric two form, symmetric pairing on lambda 2. Let's write this instead of saying so now. So this does not need any metric, right? So it's a wedge product from lambda 2 to tensor lambda 2 to lambda 4, and because I choose d mu divided by d mu, this is identified with R. It's just alpha wedge beta divided by d mu. So this is a non-degenerate symmetric pairing. And it has signature 3-3. The lambda 2 is a 6-dimensional space signature 3-3. Okay. So this factor implies that omega 1, omega 2, omega 3 span. It is a orthonormal with respect to this pairing, orthonormal basis of a positive definite three-dimensional subspace on lambda 2. Just by definition. And then it's a fact that for any positive three-dimensional subspace, you can make it standard by an element by a change of basis on the tangent space. So this is a linear algebra fact. I will make this into a exercise, a homework. So once we have this, then you just plug in this formula. This give you exactly the standard metric such that this become orthonormal. Under this basis, this E1, E2, E3, E4 becomes orthonormal basis for G. And once you see this, then immediately omega 1, omega 2, omega 3 becomes self-dual, and then we can apply the discussion we had at the end of the last lecture about the Gibbs-Hawking in a special case. So once we have self-dual, then we can define a complex structure using the form omega 2 plus I omega 3, and then omega 1 becomes a scalar form, and then it is parallel. And since we have a symmetry, so everything omega 1, omega 2, omega 3 are all parallel. So that implies lambda plus is flat. Maybe I just write on this. So then so omega 2 and I omega 3 defines a integrable complex structure. This is J, and this is the same as what we did in the special case of Gibbs-Hawking last time. So you define a 0, 1 type form alpha 0, 1 if capital omega alpha wedge omega equals 0. And we show this is a maybe I think we did for vector x contract omega vector field x of type 0, 1 if x contract omega 0. You think of omega as a holomorphic two form. And then with respect to j, omega 1 is a it's a scalar form. Excuse me. So it implies that the nabla g of omega equal omega 1 is 0, but by symmetry, so they are all equal to 0. So that implies lambda plus flat. So it's hyperkähler holonomic group containing sp1 holonomic 0. Anyway, so this just finishes the I didn't explain last lecture. Now we will go back to the Gibbons-Hawking construction. Remember, it's we have a domain. Forgot what notation did I use? Oh, omega. We have positive harmonic function. Suppose this defines a integral 1/2 pi. It's the integral cohomology class. Then it give you it's theta. It's a connection one form. On a principal U1 bundle. And then we write down explicitly hyperkähler metric is V times the standard dx V square plus V inverse theta squared. This is a hyperkähler, and it has a U1 symmetry, U1 invariant. So this is a construction, and then if you have harmonic function, we can write down explicitly. But conversely, if you have a hyperkähler metric locally, you have a kind of a triholomorphic symmetry. It's a Killing vector field, which also preserving locally. If G is hyperkähler and the psi not 0, Killing field. But this I mean psi G d derivative is 0, and also not just this, we assume it preserve each omega j. Okay, so this is actually stronger condition. Then G is locally given by the above construction. So in fact, one can recover this x1, x2, x3. This is so-called hyperkähler moment map. And so V is a norm squared. V inverse is a norm squared of the vector field, and so x1, x2, x3 is a hyperkähler moment map. So the moment map for psi with respect to each of this omega j, psi contract omega j equals d xj. So of course, each of them is only well defined up to addition of a constant, but that don't change the frame. It's a derivative, and theta is a dual one form for psi. So locally, if you see this, then you can define these objects, and then the point is the v will be equal to this. But then we're not seeing S1 action. We just see the locally this psi generate a local action of R. It does not have to come close. Anyway, so this is not important for our description of examples, but when we understand the hyperkähler matrix, this is we want to do analysis. This is important because if you can produce some symmetry, then it reduces to harmonic functions. So the hyperkähler matrix, it means a special case of Ricci flat matrix. Ricci flat equation is very complicated in tensors, and the hyperkähler equation, as we described just now, it involves this a triple of two forms. It's slightly easier because the equation only involves one derivative. This equation is algebraic equation, but this is a differential equation, just a first order equation, but it's still complicated. But once you have a symmetry, a local symmetry, then it becomes a linear equation in a function. So this is important. So here you see the equation is linear. It sounds linear, but this condition is very nonlinear. Anyway, I think then we wrote down some examples. We will write down more examples. The first one is when take omega to be the whole R3. We also said if V has a pole, then we will get a fixed point, 1, 2R. And then this what we get is a flat metric, R4, fibers over R3. This is the Hopf vibration. And then just by simple change of V, just adding a positive constant to V, we get the so-called top knot metric. So R4, R3. It's not flat. It's not the standard one, and it has cubic volume growth. At infinity, it really looks like R3. So the fibers does not grow. And if you take any complex structure, take any complex structure. So we have three complex structures. We have S2 family of complex structures, compatible complex structure. Then what we get is R4 with this complex structure J as a complex manifold is known to be biholomorphic to the standard C2. So this is non-trivial. So it's really from the complex. You can view this as Calabi-Yau metric on C2, the Ricci-Kähler metric. C2, non-standard. So not flat. And then next example, so what we call Calabi Eguchi-Hansen. Eguchi-Hansen metric. So Calabi is a mathematician. They are physicists. that's constructed independently and around similar time with different motivation. Anyway, so again take omega equals R3. We notice that the equation is a linear harmonic function. So instead of taking one Green's function, we can add two of them. So V equals 1 over 2 x minus x0 plus 1 over 2 x x1 x2 x1 x2 are two distinct points in R3. This is still a solution, and then the resulting hyperkähler manifold will have two fixed points for the S1 action. So this P we get the maps to R3, right? But generally just circle. So R3, but the R3 have two special points, x1, x2. So above any point except x1, x2, you see a circle, but over x1, you see a point. Over x2, you also see a point. So this space, this metric is called the Calabi-Hansen metric. But then the space has topology. If you just choose a line segment connecting x1 and x2, then upstairs we will see like the family of circles, they shrink to a point in both ends. How do I draw this? You will see, let's use this. So you will see something like this, right? So above each other point in the interior, you see a circle, and then the circle pinch two points at the two ends, and it's easy to see that this is a topologically it's a two sphere S2, and this two sphere is non-homologous zero, non-trivial in homology. So topologically, it is a non-trivial thing. So topologically, it is actually the same as the tangent bundle, the cotangent bundle of S2, same as tangent bundle. Total space of the tangent bundle of S2. And then, so geometrically, what's going on? So we inside x1, in the finite region, it's complicated. But if you consider x is very big, then this we have b equals 1 over minus x1 plus 1 over 2 x minus x2. So when x is very large compared to x1, x2, we can think of x1, x2 as very close to 1 point. This is like 1 over 2 over times 2, right? So you have 2 point charge in finite distance, and then you feel very far away. Then it looks like a 1 point charge. Sorry, the 2 point at the same point. So when x is very large, above is like this, and this is what we know. It is if you just use this, it is give you the metric which is R4 more Z2, because you have 2 here. If it's k times the standard function for R4, then you will get R4 more ZK. So this is the Calabi equity. Calabi equity Hansen metric. It's asymptotic to this cone, R4 more Z2. in other words, itself, it looks like this. Something which is looks like a cone at infinity, and it has topology. This is S2 inside. Okay, so this is what sometimes people call it ALE, asymptotically locally Euclidean. At infinity, it is locally Euclidean. It's a quotient of the Euclidean space. So you see, I mean, this is just a basic static electricity, right? So consider this as point charges. And you can also think of another way is that you can also make x1 goes to fix x2, fix x1. Let x2 tend to x1. Then the V will converge to this globally. It's not just approximate. It's everywhere converges to this thing. So it means that the metric converge to the flat cone in a suitable sense. And geometrically, it just corresponds to you. How do you make them come together? You just scale down R3, right? You scale down R3 in the limit that the x1, x2 collide becomes a multiplicity 2 point. But then in this four-dimensional picture, it just corresponds to you know this is asymptotic to this cone, but you can if you scale down the metric, you will get you will converge to the asymptotic cone. This is another way of understanding this. So this geometrically, it is quite different from the previous example top knot, right? And now, so one can understand it's a complex geometry. Again, this will depend on the choice of a compatible structure. Compatible complex structure. So remember the complex structure J alpha will correspond to omega alpha, right? So alpha is actually in S2. The alpha 1, alpha 2, alpha 3. Then this omega alpha is just some alpha j omega j. So it's the complex structure parameterized by element in S2, which is a direction in R3. Now we have special points x1, say x2 here, right? So there's a special direction, which is the direction along the segment of x1, x2. So if alpha is not parallel to, if alpha is parallel to x1, x2, this is either just one direction or the opposite direction, then one can check that the S2 we get, which is defined to be the pi inverse of the segment x1, x2. It's pi is mapped from P to R3 projection. Okay, this is a special S2. This S2 is holomorphic. And conversely, so this S2, the special S2, is holomorphic if and only if the complex structure is chosen to be so that alpha is parallel to x1, x2. So, but then depending on whether this is holomorphic or not, you get different complex manifold. So if alpha is parallel to x1, x2, this is holomorphic, and then one can see that the complex manifold is equal to the holomorphic cotangent bundle, which is of CP1. It's O negative 2 over CP1. So this has a natural holomorphic X2, which is 0 section of the vector bundle. If alpha is not parallel to X1, X2, the complex manifold instead it's a hypersurface inside C3 given by X say U1 squared plus U2 squared plus U3 squared equals 1 inside C3. It's a two-dimensional complex hypersurface isomorphic to this. Because it's a sub variety in C3, it cannot have any holomorphic complex submanifold. No holomorphic S2. It's another interesting exercise to see that this is actually diffeomorphic to the tangent bundle or cotangent bundle of S2. So this is complex, right? So there's a U. If you write U equals let's say cosine plus I eta, and then the condition is that this is the same as cosine eta. It's a real three-dimensional, a three-vector, 0, and the cosine norm squared minus eta norm squared equals 1, and then you can easily correspond this to a element in the tangent bundle of S2 inside say, R3. Normalize cosine, get an element in S2, and then eta is perpendicular to cosine, so it's an element in the tangent space. Anyway, so this is an interesting, very interesting and important example of hyperkilometric from the Gibbons-Hawking construction. And then there's some generalization. It's called a multi-Eguchi-Hansen. So the copy Eguchi-Hansen. It is oh, by the way, so Eguchi-Hansen's construction is does not really use complex geometry. Calabi construction really use complex geometry, and it's really it's a metric using this complex structure, so that it's a line bundle over some compact Kähler manifold, and this is a much more general thing called Calabi ansatz, which construct metrics on a total space of a line bundle over something, and it's given by partial bar of a function of the norm squared. So this Calabi ansatz is much more general. Let's go back. There's a multi-equation just means instead of take 1 point, take a k plus 1 distinct point in a 3 space, and you do this because it is a linear equation. You just superpose as many as you want. Then what you get is it's a multi-Eguchi-Hansen. So such a space, if you for generic complex structure. So of course now the complex special direction, just not for any xi xj you get a special direction. But if you avoid all these generic complex structure, what we see is a So affine subvariety in C3 given by something like x1 squared plus x2 squared plus a, sorry, so use u, u1 squared plus u2 squared plus a, say degree, k plus 1, u3 0. Equals 0, smooth. Okay, it's a smooth one, so you have to have some constant term. So previous case is just a u3 squared minus 1. So this is the complex geometry, but if this complex geometry becomes special, then things get a bit more complicated, more interesting, and you can understand the geometry at infinity. It is also ALE, the matrix ALE, and it's asymptotic to now. When you are far away, then you looks like you have one point you have k plus 1 charges, so it's R4 mod z k plus 1. Yeah. And here is also interesting to, I mean, you can analyze, for example, you can let these xi's move, and for example, let just two of the xi's collide, then you will form some singularity, and that singularity is modeled if just two of them collide, then singularity will be modeled on the Iguchi-Hansen example. Right. So these are there's a lot of interesting things you can just try to understand by working with these points in R3, and they are important in understanding more generally the local models for the singularity formation. And you can add a constant, just like the Euclidean case. You add a positive constant here. What you got is multi-top knot. So just V plus 1. Okay, so this will live on the same manifold or even same complex structure because again, so the metric expression, the two forms expression only sees the derivative of V, does not see the the connection one form only see the derivative of V. So and that's that determines the topological structure. And in fact, the complex structure only also does not depend on this addition of a constant. It's the same complex manifold, but the geometry is different. Same topology and the complex geometry as multi-Calabi Iguchi-Hansen. But geometrically is different. Geometry is what's so-called ALF, asymptotic locally flat. Just means that so like top knot we know it's asymptotic to R3. So here it's also the asymptotically. You also don't see this K because whatever you add here, when X is very large, it's very small, so it does not contribute asymptotic to R3. So topologically it's complicated. The complication depend on K, but geometrically this complication all disappear if you shrink the space. It all goes to R3. So this is called a multi-top knot. So here we get some examples of hyperkiller metrics. They are not just of course they're not compact. However, they are complete. So these are complete metrics, and they belong to what is called a gravitational instanton. So this notion was first introduced by Hawking in 1977, study Euclidean quantum gravity. So again, these are Euclidean version of the vacuum spacetime with zero cosmological constant. More precisely, in geometry, what we define as is just a complete four-dimensional Ricci flat metric G with some curvature decay at infinity. So so in order to make topology finite with the total square norm of curvature finite. Okay. So so the previous example, they all have this they're all gravitational instants, and they are they're all type 1. So of course we defined type before, so the hyperkiller ones are type 1. Meaning that W plus higher than equal to 0. So if this condition is removed, then the topology to ensure topology finite. Because this is another interesting is that the previous example, Gibbons-Hawking on R3, we can take a finite many points. We get a multi-Eguchi-Hansen multi-top knot. But we can also take infinite many points. X1, X2, infinite many points. Multiple points, whatever. Then things can be very interesting. It is shown. It was shown by, I think, by Anderson, Kronheimer, in the Brown. This around 1990s. If you just choose, you have to choose this suitably so that the metric is complete. The point has to kind of diverge. The distance have to go to infinity in some way. So what you get, you can get a gravitational instant with B2 equals infinity. Because you have infinite many points, any 2 points will, the segment connecting them give you a 2 sphere. And they are not homologically, I mean, there are some relations, but the homology they generate will go to infinity. But at the same time, the L2 norm of curvature is also infinity. So that means that the curvature, and also the curvature does not really decay very much at infinity. So this explains why we care about this example. And just to mention that this hyperkiller gravitational instance, or in general, gravitational instances have been widely studied in mathematics and physics. So there are many examples, many constructions and examples from mathematics and also physics. Aside from Gibbons, aside from Hawking, we have Gibbons Hawking. I mean, their goal was to construct and classify some gravitational instances, and also there are many people. Atiyah Hitchin, they construct this using modular space of monopoles, and then the hyperkiller quotient construction. Hitchin and other people. So you can use gauge theory, hyperkiller quotients to construct them, and also Kronheimer. He did the AL. He basically constructed and classified the ALE hyperkiller gravitational instance. It's related to the McKay correspondence for the ADE singularities. And then there are many others. Also in mathematics, you can solve PDE. The Calabi-Yau formula. And it's only recently, at least in the hyperkiller case, it has been classified, completely classified, and it goes to the hyperkiller gravitation. Classified recently. So it goes to several families: the ALE, ALF, ALG, ALH, ALG star, ALH star. So this what are these? This is just so first the ends, right? The ends are must belong to the following 6 families. So LE is locally, at infinity is R4 modular some gamma. Previous examples of this multi-equidistant gamma equals ZK, but the gamma could be more complicated. And ALF, so it's like S1 times R3. Sorry. It's asymptotic to R3, I just say. And locally it's S1 bundle. But globally there's a twist. There's a multi-top knot. But that or R3 more Z2. This is a locally R3. The Atiyah Hitchin example. This and ALG just means it goes to 2-dimensional flat. So locally, just right locally, it's just a product at infinity is product T2 times something in R2. So it's at infinity as a flat 2 torus, asymptotic to a flat 2 torus vibration over a 2-dimensional space. So of course you can just take a T2 times R2, but that's not going to have interesting examples asymptotic to that. Some positive mass obstruction to that. But the one interesting example is you take for example, if you take a region a sector in R2 with angle, say, pi over 6. Okay. So, and you take a 2 torus T2, which is the hexagon torus. It has symmetry, rotation symmetry by exactly by this angle pi over 2. So what you do is you take a T2 times this, take a product of this. Okay. So then you have 2 boundaries. Let's ignore this thing because we only care about the region near infinity. That's the asymptotic model. And then you have to glue the 2 boundaries part suitably, because when you on this flat R2, when you go around, when you identify these 2 boundaries, there's a holonomy, is a rotation by angle pi over pi over 3 or 6, not 60 degree. That's a rotation by pi over 3. So that's not if we just do that, it's not SU2 because it's like a e to the I pi over 3. If we just do this in one component, this is not going to be in SU2. You have to compensate that by a rotation in the back direction by e to the negative I pi over 3 on the T2, because T2, this T2, special T2 has this symmetry, so you can rotate. So that's a flat manifold, which is hyperkähler. So one has to be careful. A hyperkähler, of course, is W plus equals to Rich equals 0. So if something is flat, there's no curvature. So locally it is hyperkähler. But if you have non-trivial loops, then the metric may not be globally hyperkähler. It is globally hyperkähler only if this discrete part of holonomy also lies in SU2. That's why here, I mean that this you need to take some special torus. You have other special torus too. Anyway, so this ALG, so this has a quadratic volume growth at infinity. The thing at infinity is a 2-dimensional cone. Okay, asymptotic to 2D flat cone. Like in this case, because the T2 it does not grow, right? When you shrink down, you will just converge to a cone, which is just identifying these 2 sides of this sector. You get a cone of angle pi over 3. And the ALH, this is easy to describe. This is just a 3-dimensional torus times say 0 to infinity. It's a cylindrical type. So this is asymptotic to a 1-dimensional cone, which is just a ray. So these 2 families with the star is more complicated and it's more interesting. So this has an interesting topology. So it relates to Neo manifold, which is a circle bundle over a 2 torus, twisted circle bundle over 2 torus, and infraneo manifold, which is a circle bundle over a Klein bottle. Okay. So so in the end, this was classified by me and Robin Zhang, my former postdoc. So the point is that with all these models, you see that they have some description of this end at infinity, and this end, they all, this important thing is that they all admit local symmetry. And that's how why this classification is possible is that because it has you want to produce some symmetry and infinity. And once you have symmetry, then you can describe them using Gibbs-Hawking in terms of a harmonic function in three-dimensional. And then all these have local symmetries. Like here, this Neo manifold, they have circle symmetry. Infra Neo manifold, if you pass through a finite cover, it will have a symmetry. Just before we take a break, let me just show you. This is some. Can you see? This is some pictures of This is the AL. This is the ALH star. This is LG star. So these two families, their geometry at infinity is more interesting here. It is asymptotic to array, but it's not like this cylindrical case when it's just a flat, the constant size at infinity is boring. Here, when you go to infinity, since it's so each cross section, a three-dimensional manifold, is a Neo manifold. It's a circle bundle over a two-dimensional torus, and as you go toward infinity, the base torus is expanding, and then the circle is shrinking, and the volume of a ball radius r goes like r to the 4/3. It's not a integer. In the cylindrical case, it just grew like r, right? And this ALG star case is similar. It's it is something. It's a torus bundle over some cone, but this torus is not like a flat torus. It's on one circle is expanding, the other circle is shrinking. So maybe we were so these models that correspond to also interesting construction using the Gibbs-Hawking. You can easily construct these models. That's maybe after break we can explain this a little bit more. So maybe so okay. So I was talking about this showing you the picture of this LG and star and LH star, and their asymptotics to describe them globally, and the entire space is bit more work, so we will not do it here, but we will describe it as asymptotics. So this involves asymptotics of AL T star, H star. Again, using Gibbs-Hawking. So this time, we will have to apply Gibbs-Hawking to such more general three manifolds, not just a domain in R3. But if you look at the formula, if we just have a flat three manifold, the Gibbs-Hawking answer does not really work because you need to be able to write the three one forms. So you need a frame. So for example, so besides R3 as a flat manifold, we have other flat manifolds, which is a compact one times non-compact. For example, T2 times R, or S1 times R2. Okay, so if you view T2 as a R2 portion by some lattice, and S1 is R1 portion by Z. So if you just fix the standard framing, so the coordinates, standard coordinates, so their universal cover is R3. So then coordinate does not descend because you have this quote. But the framing, so dx1, dx2, dx3 still descent. And that's all we need to write down the Gibbs-Hawking. For simplicity, we will normalize so that the area of the area let's normalize. So you have a flat macro normalized so that the area of T2 equals 2 pi. So that's just the area of this lambda and the area of S1 1. Just to make things expression slightly simpler. And then what we need is a positive harmonic function. But then you can easily see that there's no positive harmonic function on this basis, even with point singularities at in the interior. So you cannot have a slow like in R3. You can have this one of R. That was a Green's function. There's no positive Green's function. The Green's function on this spaces, they actually go to negative infinity at infinity. However, if we only care about so that's why we cannot just construct complete matrix from this space, but we can restrict to some region and then we control the end. So on T2 times R, instead we consider T2 times 1 to infinity, and we call this coordinate X, Y, and Z. It's clear that a linear function is harmonic. So, but the X and Y, they're not harmonic. They're not functions, right? So only Z is a function. Just take Z. So actually, you can take V equals KZ, where K is a positive integer. And you can check the star dV. This condition is held. Let's call this Q. QZ. And so this will give you a end P over Q. So U1 bundle of Q is hyperkähler metric, and this is the ALH star, and it has K. And just from this, you see that the space, the geometry, as I describe here, because as Z goes to infinity, the circle has like 1 over square root of Z that has to go to 0. But this space T2, we have to multiply by V, right? That's expanding. So remember the Gibbs-Hawking is the base metric gets multiplied by V and the fiber gets multiplied by V inverse. And this is the this is the geometry of this LH star K and the complex geometry is even more interesting because it has a different again this is like the what's called the Gucci-Calabi-Hansen case. So before that, so when we do Gucci-Hansen, when we do Gibbs-Hawking, I have to choose a connection one form, right? Choose a connection one form. Previously, this connection one form is essentially uniquely determine up to gauge equivalence because the space, if we take R3, remove a few points, the space has vanishing H1. But now the H1 of the space is not zero, so this in general is not unique. You have to choose. Namely, you can add a flat connection to theta, but the fact that space of flat connections here is exactly T2. It's not trivial. Anyway, so you have to make a choice. So complex geometry. Let's describe this a little bit. This I think is very interesting. Complex geometry. So there are many complex, but one complex you can choose is you can choose complex structure such that you have this P maps to Q, which is T2 times 0 to infinity, and you further project to T2. But T2 has a natural complex structure from the, it's a two-dimensional flat space, right? The metric determines a unique complex structure given by a Hochstar. And so you can choose such that this composition is holomorphic. Okay, so then this becomes a holomorphic fibration over T2 is a holomorphic. What is a fiber? The fiber is just S1 times 0 to infinity. And this can be identified with some punctured disk bundle over T2. And this is actually sitting inside a holomorphic line bundle over T2. This holomorphic line bundle of degree K. So just draw the picture. So here, this is T2. This is T2. Okay, this is L, and your space P is so you have this T2 has a this not L has a zero section. So this space choose a color. Maybe this one. Is actually is inside the unit some disk bundle. Unit disk bundle inside L. So each fiber of L you choose a puncture disk, and the puncture disk is given by a disk remove the zero section removed. So this is P. So that means this P has a natural compactification by adding the zero section, right? Naturally compactified at the complete end. Compactified at the complete end by adding zero section. So this gives a model for complex geometry model for this. And again, because this P can be viewed as a subset in a holomorphic line bundle. This exactly construction is a special case of the Calabi ansatz. Special case. And it occurs so if the local model is a ample line bundle removed in the zero section, and it gives so-called the model for a more general for construction of a actual LH star actual LH star gravitational instantons. Can be constructed and actually because of classification it's not just constructed. Actually, they're almost all constructed in this way. You take a del Pedro surface, which is a complex surface with the first chain class positive, two-dimensional, and D is a smooth divisor in minus kx anti-canonical divisor. For example, x equals CP2, D is a cubic curve, smooth cubic curve. Okay, so why you can do this is because you take your x, you take your D, so you want to construct a hyperkähler metric on this complement, and then the point is that a neighborhood of D, this is can be approximated. It's not there's no tubular neighborhood in complex geometry, but you can approximate this by this normal bundle, which is an ample line bundle, and you are removing D. That's the same as this ample line bundle, and let's call this L removed in zero section. So if you remove this neighborhood, just this part is approximately can be approximated by this. It's just a linear approximation. Okay, so we have a Calabi ansatz. We have this Gibbons-Hawking from the previous one. We can graph this metric. This is a model metric back here. You get something here, and then you can solve the Calabi equation, Calabi-Yau equation, to get a Calabi-Yau metric. So that's the but we don't know much about the geometry beyond this region, but in this region is well approximated by this model. This is one complex structure, but you can also choose another complex structure. You can also choose a complex structure such that this projection we have P to T2 times 0 to infinity, and I can pick S1 inside T2, get S1 to 0 to infinity. Okay, so I can make this holomorphic. So what is this? This is just also a punctured disk, but here this S1 is a base. S1 in T2 previously, the S1 this is S1 fiber from the Gibbons-Hawking, right? I can make this holomorphic. And then the fibers will be, you have one you have a circle over here, circle bound over here, and then you project to one S1. Then what's remaining is a circle bound over a circle, which has a torus. So fibers are elliptic curves. So what we get is a so-called elliptic vibration over the puncture disk. And one can check that this monodromy is equal to it's type IK in the Kodaira classification, but the monodromy is something like a 1K01. So what is a monodromy? So it's similar to as described before, right? You have a T2 vibration over the puncture disk, so you can take you can fix a one fiber T2. You fix the basis of the H1 of T2 Z2, and then you just as you move around, this one circle may become a different circle. So then you expand the what you get after you rotate. After that circle write that circle in terms of the basis. That's the so the one row vector, and they have another circle. You get a matrix. It's very similar to holonomy, except here you are just you are doing topological transport. So and then you have I mean you can also be compactified by adding a singular fiber. So you go around, so the smooth fibers are like this, but the singular fibers, because you see, if you add something in the at the puncture, if it's smooth, then it has to be invariant under the monodromy. But this monodromy has only one invariant direction, one invariant vector, right? The other one gets shifted, so it cannot be smooth, and instead it becomes a nodal elliptic curve. So so this direction, this circle still survive. So you still have a rotation along this blue direction, but the other direction there's no rotation. Because they're singular, there's pinched. Okay, so one of this blue, one of the blue circle gets pinched, so that means the other S1 action is get destroyed. Anyway, so this is a vast subject about elliptic singularity, elliptic vibrations that was classified by Kodaira. But so that means you have another way of constructing this instance LH star gravitational instance starting from elliptic vibrations. So this was something done by Hayu Hai, his thesis. As you are Hai thesis using so-called rational elliptic surfaces. Okay, so this is ALH star, and ALG star will be just a bit brief. ALG star, what you can do is you take S1 times R2, remove a ball. Let's say it's one ball, and you take a V to be, so you have no function S1, you have a harmonic function R2, which is a log R. And of course, you can multiply by K. K is a positive integer. And in this way, you get a ALG star, and but then this whole thing has a, so you get call it ALG star IK P, but then the whole thing has an involution. You can take P more Z2 involution because you have Z2 action on S1 on the base. That's a natural involution, and then you can lift it to the total space. This is called ALG star, IK star. And this is more interesting because if you just look at ALG star IK, there's no such a complete example. This anyway, so this is give you some torus bundle over a two-dimensional thing, and the torus self is degenerating infinity. So this finishes this discussion of hyperkiller gravitational instants and their end structures. So and the classification, on the one hand, it depends on the fact that the classification before. So we already know. Suppose we know that it has these 6 families, right? And over each family, how do we classify? It uses connections with complex geometry. It uses compactification. Just like what we described. It's true, actually, every hyperkiller gravitational instant can be compactified. So MG, you can choose a complex structure. That's when we do complex geometry, we have to choose a complex structure J such that as a complex surface, this is some compact thing removing a divisor. It's a compact algebraic surface. This is a divisor. And then you can use complex surface theory to try to come back. And then another thing is they all, I mean, each family arise from degenerations of hyperkiller matrix on K3. Which is compact. So all these gravitational by definition they're non-compact. Maybe I should just add this explicitly. We assume they are non-compact. I said complete, but it should be assumed non-compact. Okay. There's the compact ones. So next we will talk about the compact ones. This was actually quite closely related. But we cannot use Gibbs-Hawking to construct the non-compact, construct compact gravitational instance because Ricci-Fine metric. The first lecture we talked about is Ricci non-positive. So if you have a Killing vector field, a compact case, if you have a Killing vector field, it has to be parallel, and then by some a little bit more theory, you see it has to be flat. That's 4-dimensional case. So we are interested in non-flat examples. So I cannot have any global Killing field. But they are related to compact. These non-compact ones are related to because when you have a compact matrix, they may form singularities, and then near the singularity, if you zoom in, expand, then you will see this non-compact objects. So actually, you can use this gravitational instant to construct a compact example. That's next thing. So let's define so compact hyperkiller four manifolds. So this is a fact. Okay, I will not prove it. It's not. It's actually a bit deep. They have to be diffeomorphic to either the K3 or the 4 torus. And in this case, it's a flat, so we're not interested in it. So what is K3? K3 is a simply connected. And let's just take a model. So it's K3. If you do complex geometry, it's a particular surface which is given by quartic. So Z04 plus Z14 plus Z24 plus Z34 equals 0 inside CP3. Okay, so it's a diffeomorphic to this, and it's known that all the K3 surfaces are diffeomorphic. Let's just take this as it's oriented four manifold. Right? It's a standard orientation from the complex structure. So we know that the existence of a hyperkinetic on K3 is given by Yau's theorem, proof of Calabi conjecture. We will probably explain a little bit more in the last lecture. We will talk about the last lecture. We will focus on Kähler geometry. But the point is that this is it's a PDE proof. It's non-explicit or non-geometrical. And that makes it hard to understand the geometry, and also if you're interested in physics, to do explicit calculations is almost impossible. But there is also a more geometric way of understanding hyperkinetic by using so-called gluing methods. So let's just let's do the Kummer construction, not the Yau construction, the Kummer construction of one hyperkinetic on K3. How do we do this? So you take a flat 4 torus. Okay, so this is hyperkinetic, but the bad thing is that it has non-trivial. It's not simply connected. So, and that makes it there's some splitting theorem. So it's a rich flat, and then it has to be flat. So we have to kill the homology. And one way to do this is you mod by Z2. Z2 is involution. It's just a map. So X1, X2, X3, X4 to -1, X2. This is the Z2 action. There's involution. Involution. Okay. So once you mod by Z2, it becomes actually becomes simply connected. It's the standard examples. If you take a T1, which is S1, you mod Z2, you will see it is a it has two fixed points. Just do this solution. Okay, has two fixed points. So what you get is a interval. Or if you take T2, it's S2 mod Z2. It again has 4 fixed points. So sorry. I'm doing T1 mod Z2. Doing T1, which is S1. Okay, but T2 is not S2. T2 mod Z2. If you take T2, you take the involution, and then this is the a standard fact that the two torus is a double cover of the Riemann sphere branch at the 4 points. What you get is S2. It's simply connected. Okay. Anyway, so you can do T4 more Z2. This has 16. So orbifold points. Locally, it's modeled by R4 more Z2. Okay, so let me just draw it schematically. It's something like this. It has singularity. Here I only draw 4 of them. You have 16 of them. So you want to resolve these singularities. You want to make it smooth. But how do you make it smooth? You have to put in something else. You have to cut, right? So this is you have to cut this part. Remove this part. Let's do it. You remove a neighborhood of a singularity. And the neighborhood singularity is modeled by this R4 mod Z2 is S3 mod Z2, right? But you have to put in something else. You want to put something else, which still satisfies the hyperkiller equation. Still hyperkiller, you shouldn't put something random. Even you put something hyperkiller, then when in this grafting region there will still be some error, and then you have to do some analysis to perturb it, some implicit function theorem to perturb it to a hyperkiller metric. But we have a candidate. If you follow closely, the first half of the lecture, I spent a lot of time talking about Eguchi-Hansen. Calabi Eguchi-Hansen is exactly used. So this is the picture I draw, right? So this is R4 mod Z2 at infinity. So this R4 mod Z2, you can cut something here, and then you can put this here. Of course, just look at this picture. It does seem doesn't look like you can put it back because this is very big, and there singularity is very small. But what you can do, you have to shrink this. Let's see if I can. No, okay, I don't know. You can you have to shrink. You have to shrink this part, make it small, and then you put it here. So it will be something like. Okay. So because this is possible exactly because the asymptotics at the infinity of the Calabi-Hansen agrees with the asymptotics at the singular point of this orbifold metric. So you grew in 16 Eguchi-Hansen at each one at each singular point, and then you get something which is approximately hyperkiller. It is hyperkiller except at these green regions when you introduce some error and then you use implicit function theorem. It's this is an important thing called the green construction in geometry. It can be done for many geometric structures. It's easy. It's always easy to say. The strategy is simple, but to actually realize the construction, it takes a lot of effort. But anyway, the point is that here we can actually do the green construction, and we will get a hyperkiller metric which is simply connected, and then it is and topologically it is a K3 because the topology is you can see that the explicit representatives of the homology. So But it's not just one, it's a family of degenerating hyperkähler matrix. Okay, so this is why this is more geometric, because it does not just give you one example, it gives you a family, because it's constructed, you can choose a parameter as small as you like, actually. So you get you can see there's a family of this hyperkähler matrix on K3, which is forming such a singularity, and the mechanism of forming this each singularity is exactly because there's this Calabi equation Hansen, which shrink to a point. That's the geometry. Let me. Right. So there's a green construction. It is geometric, but it only give you some metric in some region in the moduli space of all hyperkähler matrices. It have to be degenerating, and this here I did for Calabi equation Hansen. This is just ALE case, but so for all these families, LE, LF, LG, LH, G star, LH star, they can all model such a degeneration. So at the end of this lecture, I will show you another picture of LH star coming out. But before that, let's talk about more about K3. So as I said, there's no single formula known for a hyperkähler metric on K3. Even the green constructor does not give a precise formula. But the moduli space, what is this? This is that's denoted by M. This is a hyperkähler matrix on K3 with we can always rescale. We fix this normalized diameter equals 1. Okay, there's such a space. We modular equivalence. Let's take the diffeomorphism modular 0. Diffeomorphism that's isotropic to the identity. Okay, so this is a moduli space, and the good thing is this moduli space actually can be explicitly described. It has an explicit description in terms of Torelli theorem. Torelli theorem. Meaning that it can be described in topology. So let me describe this. How do we do this? So if you have any G, it's hyperkähler on K3, and the K3 is known as it is K3 Z. So this is second cohomology is isomorphic to 3 of this matrix 3U and 2E8. Its rank is 22. Okay, so E8 they are negative definite. I don't know if and then negative E8 may make negative definite. So its signature is 319. The 3 positive from here. All the others. Okay, this is some topology. So it means in the in H2 K3 R. So there's a what's the the wedge product. Sorry, the Poincare pairing. If you on H2, K3R is just a quadratic symmetric quadratic two form with thickness 319. So that means you can have three-dimensional positive subspace here. If you have a hyperkähler metric on K3, then we have omega 1, omega 2, omega 3. This is self-dual harmonic forms. Two forms, right? And because it's so this omega I wedge omega j at each point is delta ij d mu. If you integrate it, this is just a delta ij times the integral of d mu, right? So the each omega I has a cohomology class. This is just exactly omega I cup. No. 1/2 equals delta ij times d mu. So that means this is three cohomology class, omega 1, omega 2, omega 3. This is span a positive three-dimensional subspace in H2 K3 R. We call this let's call this space HG plus. So this is just depending on G, right? If you have a hyperkähler metric, you have this two forms and three cohomology class. If you change the metric, you will change the class. So you get a period map. P from this modular space to the period domain, which is GR plus 319. So what is this? This is a three-dimensional positive space, the Grassmann of positive three-dimensional subspace in the R22 in the second cohomology. So it's just send G to HG plus, and we are modular by the Diffie-Morgan's isotopic identity. So that's in this case, this does not change. It does only depend on the equivalent class. So you have a period map. So each hyperkähler metric give you something in this fine-dimensional symmetric space, and the Torelli theorem says that this P is injective. So the hyperkähler metric is uniquely determined by this period, and surjective except some special surjective on the subspace with D minus is a bit complicated. If you take any delta in lower H2 K3Z, delta equals -2. So it's just self-intersection -2 homology class. And then if everything is perpendicular to that, we have to remove it. So delta plus perpen is defined to be all H containing H2 K3R 3D-dimensional subspace such that the integral of everything in H over delta is 0 for all alpha in H. Okay, so this is defined exactly to be the so this is a countable union of some linear subspace in Grassmann. So the Torelli theorem says it is Surjective here, and what's this? This corresponds to if you add. So from this we already see the dimension. This modular space has a dimension. Dimension is dimension of D, which is 3 times 1957. Okay. And how do you make this? How do you fill in these holes? And then that's you just add it's partial complement by adding orbifold. So M bar is compactification of M and so-called Gromov-Hausdorff topology. All right, so that's you don't have to know that what is this. It just means you have a matrix with a bounded diameter here. You can take limits, but the limit could be lower dimensional. For example, if you take a circle, you can shrink to a point, right? Such a thing. But there's a partial compactification. You just the combination and by sorry, just it's just a m together with orbifold limit. So orbifold limit means that you only consider limits that have the same dimension as 4 dimension. These spaces that have orbifold singularities. The T4 mod Z2 in the Kummer construction, that's something we exactly of this form. And then the point is that the P it extends to M bar partial to the domain D. This is bijective. Okay, so this is if you want a bijective map, that you're just adding this orbifold limit. So that means this case hyperkähler matrix on K3 plus its orbifold limits, they can be characterized in terms of symmetric space. And for the other part, M bar, this you can understand them because me and Robin, we actually can classify limits. And one can understand the behavior of a period map. Can be understood, and then it's exercise. You can exercise. You can try to use this period map to relate to some compactification of this period domain. So it's a work of Odaka and Oshima and others. So okay, 4 more minutes. So this is relation with K3. And then going back to general gravitational instance. General gravitational instance. It's more complicated. So type 1 is central classified, and then there's type 2. This was also classified, essentially classified. Okay, there are still some cases not completely done. In the LE case, by Mingyang Li. It's real. Okay. That's a preference on this. And here you have something which is more original from physics, Schwarzschild occur. These are all Euclidean solutions. Okay, matrix, and then you have anti-top knot. Means I take the top knot metric, but if I change the orientation, then it's no longer hyperkiller because W minus is not 0. When you change orientation, W plus is not 0. And anti-Calabi-Hansen. And something called top bolt. So and then there was a interesting example constructed by Chen Till in around 2011. So that was in relativity, there's a black hole uniqueness theorem. I mean for there are various versions, but I think that the most general version is still not known, even in the stationary case. When you have multi black holes. So but you believe that there's some uniqueness statement that if you fix something at infinity is asymptotic flat, then you have uniqueness determined by mass, momentum, charge, whatever. But then Chen Chiu, they construct the example which is a counter example to the naive version of Riemannian black hole uniqueness. You just take the statement of black hole uniqueness, and you go to the Riemannian signature. This is known to be false. That's very interesting. And then this is my own work. That's advertisement. Type 3, meaning that the YW plus has generically 3 different eigenvalues. That's essentially no examples, no. And there's a work by me and Ming Yang this year. We use relation with harmonic maps. Gives examples, but not this first step of understanding these objects. It is a difficult subject, but it could be interesting for exploration. Okay, so as I promised, I'll show a picture of something case. This is this as a K3 hyperkilometric on a K3. This thing looks like a hyperkilometric on a K3, and we normalize the diameter to be 1. And you think about the family of them, and then they are getting thinner, and in the end they collapse to a unit interval. Okay, so and there are a lot of interesting things coming up in this process because K3 has a very complex topology. Interval has no topology. So you cannot. There should be very complicated thing inside, and inside what I want to actually see is something near this endpoints. If you zoom in enough, you will see this ALH star gravitational influence, something like this. If you look at this picture, it's something you should see. And there are also these points where you will see top knot. Top knot is something topologically it's trivial. It's just R4. That's why you don't see the topology. But then it has an interesting geometry. Okay, so this finishes the 3rd lecture. The next last lecture we will focus on Kähler geometry.